Hi, linear algebra students. So this is the end of section exercise of section 1.8, Introduction to Linear Transformation. I would strongly encourage you to try this exercise yourself, but actually it is quite hard, okay? And the reason is because it uses a lot of concept. So I gave you a hint on how to prove this in your lecture notes, but I'm actually gonna tell you right now more information in order to help you in order to being stuck a little bit less easily. Let's put it this way. So first of all, let's have a look at what we need to prove. If we have a linear transformation. So first of all, we know it's linear, okay? So I will underline this in green. If the transformation is linear, and we know that V1, V2, V3 spans R3, then T of V1, T of V2, and T of V3 spans the range of T. Okay, that's what we need to prove. Okay, and the first thing I want to tell you is what does it mean for this set to span the range of T? It means that the range of T and the span of this set must be the same thing. So what you want to prove essentially is this equality between the two sets, okay? And if you remember correctly, the two sets are equal if they are contained in each other. In other words, if the span is contained in the range and the range is contained in the span, then these two sets are equal, okay? And so I'm going to jump at my bullet point number 5 just to tell you what I mean. Okay, so we're going to do the proof in 2 steps. First, we're going to prove that if y is in the range, then y is in the span. In other words, we will prove that the range is contained in the span. Okay, this is step 1. Step number 2, we will prove that if y is an element of the span, then y is also in the range. So this proves that the span is contained in the range. And as a result, if we are able to do both step number 1 and step number 2, then the two sets are equal and we prove the theorem. Okay? Now, here are the tools that we need in order to prove both number 1 and number 2. So, what's the definition of y being in the range? It means that y is an image, and an image has a pre-image. So, in other words, y is in the range if there is x for which t of x is equal to y. So, if we can find the value of x in a way that we can write something like this, then we prove that y is in the range. Y is inside the span of T of V1, T of V2, T of V3 if it's a linear combination of T of V1, T of V2, and T of V3. So if we can somehow write Y as a linear combination of these vectors, we will prove this, okay? The big final tool that we will use is this one. If T is linear, right? So note that we will use the fact that T is linear in order to use this kind of calculation, okay? If T is linear, it preserves linear combinations. So if you have like a bracket like this inside T, you can actually pull out the x1 to xk's and write T of V1 until T of Vk. So that's what it means to preserve linear combination. You have a linear combination of the vector V1 to Vk, then the answer is the corresponding linear combination of the vectors T of V1 to T of Vk. All right, without further ado, let's begin with step number 1 and step number 2. So I'm erasing the notes. Before I erase them, just take them down or pause or screenshot maybe, but take them down actually. Okay, so begin with step number 1. Okay, remember we want to show that y is in the range implies y is in the span. And I'm not gonna rewrite what it means, but I'm gonna start with the fact that I know y has a preimage. Okay, so if y is in the range t, then there is x such that t of x is equal to y. Or actually, let's write the reverse. Y is equal to t of x. That's the first argument. The second argument is this, okay? So the fact that V1, V2, V3 spans R3, okay? Since V1, V2, V3 spans R3, every vector x, so x is a LC of V1, V2, V3. So in other words, what I'm saying here is that we can write x equals, and that's it, C1, V1 plus C2, V2 plus C3, V3 for some C1, C2, C3 in the real number set, right? Okay. Following up, y, which we know is t of x, we write it as t of C1, V1 plus C2, V2 plus C3, V3. Now is the key part. We are using the linearity of the transformation. So here you go. I'm not gonna write over here. I'm gonna just write it down there. So since we know that t is linear, it means that we can pull out the constants and write the corresponding linear combination of t of v1, t of v2, plus c3, t of v3. So as a result, since y is a linear combination, like we have the linear combination right here, then we know that y is in the span, and that ends step number 1. So y is a LC of TV1, TV2, TV3, and therefore y is in the span. Okay, so just for you to follow up here, step 1 is done. We just proved that if y has a preimage, then necessarily y is in the span of these 3 vectors. Okay, now let's erase everything and we'll go on with the second step. So actually the second step, you see, it's just to revert these words, right? We want to prove that if y is in the span, then y is in the range. Okay, now I'm going to erase this immediately because this is like, it's not the second part of the proof, it's the first one. Okay. So now we start from the opposite assumption. The only thing we know is that y is a linear combination of T1, T of V1, T of V2, T of V3. So if y is, or actually let's put it this way, if y is in the span of these vectors, then we know that y is equal to C1 TV1 plus C2 TV2 plus C3 TV3 for some C1, C2, C3 in the real number set, okay? So that is because we know that y is in the span. So y is a linear combination of these three vectors, okay? Now, we're going to use the linearity of the transformation in the opposite way, okay? So in other words, again, we know that t is linear. So what it allows us to do is to compress back that linear transformation. We know that this is t of C1V1 plus C2V2 plus C3V3. Okay? And as a result, as you can see, this vector, so I will call that vector x. So x, which is equal to exactly this vector, C1V1 plus C2V2 plus C3V3, is a pre-image of y. And for this reason, y is in the range of t. So again, just to follow up on that, it means that step number 2 is done. Okay? So as a result, let's call this step number 3, all right? Okay? So in step 1, we prove that the range is contained in the span. So range is contained in span. And in step 2, we prove that the span is contained in the range. So as a final result, the span is equal to the range. Okay, and this is what we wanted to prove. Okay, I would expect a longer statement here. I would expect you to say that the range of t is equal the span of t of v1, t of v2, t of v3. I just don't want my video to take forever. So hopefully you understood. And this is it. This is the proof of this theorem. So it's the end of this exercise, in other words. I'm gonna just put a box here and see you in the next video.